So this video is just going to show some more examples of finding eigenvectors and eigenvalues using the method I showed you in the previous video. So I'm going to do 3 examples, and each of these examples shows you a slightly different, some slightly different properties of this method. So the first one is just another regular 2x2 matrix. The second one is the rotation matrix. Now this is interesting because for a general value of theta, it looks like there aren't any eigenvectors, right? Because remember, an eigenvector is a vector which stays parallel after transformation. But if I take theta, say, is about 30 degrees, then after transformation, no vector is going to be parallel. Right? So it looks like this shouldn't have any eigenvectors and eigenvalues. So what happens here? And then the third one is a 3x3 matrix, just to show you how it works for larger matrix sizes. Okay, so I'll solve these 3 in this video. Before I do that, you may have noticed eigenvectors, eigenvalues are quite long words, so I'm going to abbreviate them. So an eigenvector is going to become an e-vec, and an eigenvalue is going to become an e-val, just to save me writing. Okay, right, so let's begin. Number 1, we will need to find the eigenvalues of this matrix A. So to find the eigenvalues, you need to solve the characteristic polynomial, which is det A minus lambda I equals 0. Okay. So what is A minus lambda I? This is minus 1, 1, 2, 0, minus lambda 0, 0, lambda, which is minus 1 minus lambda, 1, 2, minus lambda. Okay, so we need to find the determinant of this. This is minus 1 minus lambda times minus lambda minus 1 times 2. So this is lambda squared plus lambda minus 2, and this should be equal to 0. Okay, so that's my characteristic polynomial right there. Again, it's a quadratic equation. And again, I've chosen a nice example so you can factorize it in the integers. This is lambda plus 2, lambda minus 1 equals 0. So your 2 solutions are lambda 1 is minus 2, lambda 2 is 1. Okay. So that means there should be a vector which this matrix multiplies by minus 2, and there should be a vector which this matrix multiplies by 1, leaves the same, in other words. Okay, so we found the eigenvalues. Next we have to find the eigenvectors. Okay, so to find the eigenvectors, the method was to solve A minus lambda I times V should be equal to 0. So the first eigenvalue we got is minus 2. So if I put lambda equals minus 2 into this equation, we get 1, 1, 2, 2. And let's say V is x, y, and this should be equal to 0, 0. You see that just, again, gives you one equation. X plus y is 0, y is minus x. So I can choose x to be whatever I like. I'll choose it to be 1 again. Then you get the first eigenvector, v1, is equal to x is 1, y is minus 1. Okay, so that's the first eigenvector and the first eigenvalue. Okay, so then we should repeat it again for the second eigenvalue. So if I put lambda equals 1 into here, I get minus 2, 1, 2 minus 1, xy equals 0, 0. That tells me that minus 2x plus y equals 0. So y is 2x, and again I'll choose x equals 1. So then I get second eigenvector, x is 1, y is 2. Okay, so that's the answer. These are the 2 eigenvalues and the 2 eigenvectors. Now it's always a good idea to check your work, so I'll just do it for this one. very quick to check. So the way you check is you should check the equation, the defining equation is satisfied. Okay. So first I'll do v1. So that gives me a is this, v1 is this. That's minus 1 minus 1 is minus 2, and 2, 0 is 2, which is minus 2 times 1 minus 1. Okay, so that works because this vector is multiplied by minus 2, which is the eigenvalue I found. Okay, and we check the second one too. So here the eigenvector I found was 1, 2. So I get minus 1 plus 2 is 1. 2 plus 0 is 2. So this equals 1 times 1, 2, which again works. Okay, sorry about the phone call interruption. So we finished the first example there. Now we'll go on to the second one, which is the rotation matrix. And as I said, you would expect that it won't have, in general, any eigenvectors because there are no vectors which remain parallel after rotation. Okay, so let's see what happens in that case. Okay, so this is example number 2. R of theta, which was cos theta minus sine theta, cos theta. Okay, so method is same. So to find the eigenvalues, you need to solve determinant r theta minus lambda I equals 0. Okay. R theta minus lambda I is cos theta minus lambda minus sine theta cos theta minus lambda. Okay, I'll do a little bit faster for this second example. Okay, so therefore the determinant of this is cos theta minus lambda squared plus sine squared theta, which is lambda squared minus 2 cos theta lambda plus cos squared theta plus sine squared theta, which is lambda squared minus 2 cos theta lambda plus 1. And we need this to be equal to 0. So again, this defines our characteristic polynomial here, which we need to solve to find the eigenvectors and eigenvalues. Sorry. Okay, so this one doesn't factorize simply, but we can find the solutions using the quadratic formula. So this is minus that, so 2 cos theta plus or minus the square root of 4 cos squared theta minus that times that is 4 all over 2. Now this is, cancel the factors of 2, this is cos theta plus or minus the square root cos squared theta minus 1. And you see that this doesn't have a real solution, right? Which is good because we said there shouldn't be any real eigenvectors or eigenvalues because of the way the rotation shifts. So it doesn't have any real solution, but it does have a complex solution, which still makes sense. So let's work out what that is. So this is cos theta plus or minus the square root of minus sine squared theta, which is cos theta plus or minus, so square root of minus 1 is I, sine theta, and then using Euler's formula, this is lambda plus minus is e to the plus or minus I theta. Okay. So we can still solve for the eigenvalues, that's these, okay. But the eigenvalues are not real, and correspondingly the eigenvectors are not real. And that's how we get around the fact that the rotation matrix, because it represents a rotation, it can't keep any real vectors the same, right? Every real vector must change direction. But if we go into complex vectors, then you can find complex vectors which do not change direction. So therefore, even though there are no real eigenvectors and eigenvalues, you can define complex eigenvectors and eigenvalues for this matrix. Okay, so let's find out what those eigenvectors are. That means solving the equation r theta minus lambda I. V equals 0. Okay, so first of all we'll do it for lambda plus, which is e to the I theta. So if I put e to the I theta in here, then I get cos theta minus e to the I theta minus sine theta times xy is 0, 0. Okay, now you can simplify this a lot using Euler's formula. Remember, Euler's formula says that e to the I theta is cos theta plus I sine theta. Okay, so you can see that the cos theta terms are going to cancel here and here, right? So you'll get minus I sine theta minus sine theta minus I sine theta xy equals 0, 0. Okay, so provided that theta is not equal to 0 or pi, in which case it's trivial because every vector is an eigenvector. If in that case sine theta is not 0, so we can cancel the sine thetas, and you get minus I minus 1, 1 minus I xy is 0, 0. Now this gives again a single equation, minus I x minus y is 0. And this second equation is the same as this equation multiplied by I. Right? If I multiply this by I get x minus iy equals 0, which is what you get the second one. Okay, so you get that equation. So this means that y is minus ix. So I think just to be different in this case, I'm going to choose x to be equal to I instead of 1. So it doesn't matter. You can choose whatever you want. So in that case, you get that y is equal to 1. And therefore, you get the eigenvector v plus x is I, y is 1. Okay. And we can do a similar calculation for the second eigenvalue, which is that. So I'll do this one slightly quicker because it works out the same. Okay. So in this case, same as this with minus theta here. So that gives you a minus I theta here. So the equation you end up with is that same as here, but with i's replaced by minus i's. So this is I minus 1, 1, I, xy equals 0, 0. Okay, so I jumped the first 3 steps to save time, so you can do that yourself. Okay, and again you get one equation, ix minus y is 0, okay, which means that y is I times x, and if I choose x equals 1 again, this means that y is equal to I. I just make this choice to have a nice symmetry between the eigenvectors, okay? And in that case, the eigenvector v minus is 1i. Okay. There we go. So that's the answer. So we found the eigenvectors and eigenvalues of this rotation matrix, and as I said, in general, these are complex eigenvalues and eigenvectors. Now you'll note that last week I talked about special matrices, and in particular I said that this rotation matrix is a unitary matrix. And it turns out that the eigenvalues are e to the I theta with some angle theta. Now this is a general result, which I'll prove at the last video this week. If you have a unitary matrix of any size, doesn't have to be 2 by 2, then the eigenvalues for that matrix will always be e to the I theta for some theta. Okay, so last we have to go on to our 3 by 3 matrix, So number 3. So that was the matrix B, which was minus 1, 1, 3, 1, 2, 0, 3, 0, 2. Okay. So again, we have to find the eigenvalues first. So that means solve det b minus lambda I equals 0. Okay. So the determinant of b minus lambda I, this is the determinant of minus 1 minus lambda. Okay. Here, lambda I is the matrix lambda 0, 0, 0, lambda 0, 0, 0, lambda, right? So we just subtract lambda from the diagonal elements. Like this. Okay, so we need to calculate the determinant of this matrix. So I can do this by expanding, and I think I will take, I'll take this one, okay. I'll expand down here, okay. And then remember the chessboard matrix has a minus for this one, a plus for this one, and a minus for that one. So the determinant of this is going to be equal to minus 1 times this. That's 1, 3, 0, 2 minus lambda. And I get plus this times this matrix. Okay, and the last one is 0, so that's good. So this gives me minus 2 minus lambda plus 2 minus lambda times minus 1 minus lambda, 2 minus lambda, minus 9. Okay, and luckily, or well, not luckily, I chose it this way. You see that the factor here is the same, so you get one solution, lambda equals 2 for free. So I can factorize that. So this is minus 2 minus lambda times, okay, so we can say plus. So then I get minus 1 from here, and from here I get plus lambda squared minus 2 lambda plus lambda, so that's minus lambda, and then I get minus 2 minus 9 is minus 12. No, sorry, minus 2 minus 9 is minus 11. That would be helpful if I can do that correctly. Okay, so this is minus lambda minus 2, lambda squared minus lambda minus 12. Okay, and luckily this factorizes again. Not luckily, I chose it that way. Lambda minus 2, lambda minus 4, lambda plus 3. Okay, so this is equal to 0. That's your characteristic equation again. And in this case, you get 3 solutions. Lambda 1 is 2, lambda 2 is 4, lambda 3 is minus 3. Okay, so these are the 3 eigenvalues of the 3 by 3 matrix B. Now note that in general, when you multiply this out, you're going to get a cubic equation, right? Lambda cubed plus something, something, something. And in general, cubic equations are hard to solve. I chose an easy example, so that's why the eigenvalues turned out to be nice. If you pick a general 3 by 3 matrix, it will be very hard to solve the eigenvalues in general. Okay, but in the exam or in the test, I will always give you a nice example. Okay. Right, so we found the eigenvalues. So next we have to find the eigenvectors, and that means solving b minus lambda I times v is equal to 0. Okay, so I don't want to spend too much time with this, so I'll just do one of them. So the first one is actually the easiest, so I'll do a slightly more difficult one. I'll do the second one. So I'll do the example lambda 2 is 4. Okay, and I'll leave these two as an exercise. So lambda 2 equals 4. So I put lambda equals 4 into this equation here. Then I get minus 5, 1, 3, 1, minus 2, 0, 3, 0, minus 2. And that times the vector v, which I can call x, y, z, should be equal to 0, 0, 0. Okay. So you need to solve this equation. And as before, one of these equations will be redundant if you've done it correctly. So you only need to look at two of these equations. So the two simplest equations to look at in this case are these. So here I get x minus 2y equals 0, and 3x minus 2z equals 0. So I think that's going to be easiest to choose x equals 2 in this case. That will give me an integer here. Right? So if x equals 2, then this first equation tells me that y is equal to 1, and this second equation tells me that 2z equals 6. So that means z equals 3. So that means that the vector v2, the second eigenvector, should be 2, 1, 3. So I solved this only using the second two equations. You should really check that the first equation is okay too. It should be, but you can check. So minus 10 plus 1 plus 9 is 0. Yeah, that's good. Okay, so that works. Right, and then you have to repeat this process for the other two eigenvalues as well. I won't show the calculation because hopefully you've got the idea by now, but I can tell you what the results is. So v1 turns out to be 0 minus 3, 1. v3 turns out to be minus 5, 1, 3. Okay, and as I said, the choice of one of these is arbitrary. So I could have chosen x equals 1 here. Okay, if I chose x equals 1 instead of 2, then I would have got 1, a half, 3 halves. Okay? So that's a bit more ugly than this perhaps, but it's still correct. So you could have this answer, that's still okay. You could also have the answer 4, 2, 6, that's still okay, or the answer minus 6, minus 3, minus 9. Okay. Any scalar multiple of this vector is still okay. For example, here again, you could have taken 0, 3, minus 1, or you could have taken 0, 1, minus a third, or whatever. Okay. These are all okay, up to a scalar multiple. Right, so that's the end of this third video, which is showing you how to find eigenvectors and eigenvalues in general. So in the fourth video, I'm going to explain why these things are so useful.